Welcome everybody to the tutorial on LSM-trees. So I'm Anso Thanasoulis, and this tutorial will be with Subhadeep Sarkar, who is working with me at Boston University. Today we'll be speaking to you about LSM-trees, and we will dive into the details of their designs and their optimizations, focusing a lot on compactions and writes, but also giving a lot of insights about optimizing for performance. LSM-trees, what are they really, and when they were designed? So maybe you'll know there was a paper already back from the 1996 where Pat O'Neill described LSM-tree, however, after 1996, there was no real use of LSM-tree for over 10 years when Google picked it up with their big table design. So why there was no big use of LSM-trees for these 10 years? Well, if we go at the time that this tree was designed for the first time, we were able to get good random read performance to arrays of disks, right? So, and LSM-tree, the main idea, as we will see today, was essentially to try to account for the fact that disks have very good sequential write performance and read performance, but not random. So this was not really a problem because we could actually get very good random performance from the array of disks. However, Google in 2006 decided to build their services on commodity hardware. So if you see even the big table paper, it says that we're going to be using one or two disks per node, and that's all. So all of a sudden, it is very important to try to optimize for sequentiality because we are getting poor ingestion performance and poor read performance for our random access workload. Enter LSM-trees. So LSM-trees offer a very fast ingestion, which is the main driver of optimization and the main driver for using LSM-trees. But also it offers competitive random reads, as we'll see through a variety of optimizations. And it also turned out to be SSD-friendly. The LSM design turned out to be SSD-friendly, essentially by minimizing the impact that it has on the wearing of the device. So since 2006, a lot of systems have actually been developed using the LSM paradigm. So we're listing a few names here: HBase, Cassandra, LevelDB, RocksDB. And today, LSM-trees are used in a variety of systems, not only as a key value store engine, as the storage engine of a key value store, but also as a storage engine for relational systems and time series-based systems. So why LSM? LSM is good for fast ingestion. It's also very good because it has competitive reads, and it is very tunable. Essentially, we can make an LSM-tree to be more optimized for reads or more for writes or more optimized for reads, depending on the tuning knobs that we will see a few of them today. Last but not least, LSM also offer very competitive space utilization. Essentially, we don't have a lot of free space that is occupying our devices. We have very low wastage space when we're using LSM-trees. So all of those reasons actually have led to the LSM-tree being a very popular topic of research since 2006. And here, with data from DBLP, we see that there is an exponential growth, essentially, of interest of the community. However, there is no digestion of these techniques that they have been developed, so there's no textbook on LSM. And one of the goals that we have here is to prepare for the community this type of material that will help understand the basics, but also the optimizations and the nuances that LSM-trees have. And today in this presentation, we will serve both audiences that don't know anything about LSM and they want to learn how they work really, and also audiences that know a lot about LSM and they want to find out some of the most recent optimizations and new techniques that are being developed. So the remaining of the tutorial is going to be in three parts. We'll first define what LSM is and the operational principles of LSM. Then we will talk about the most key operation, which is ingesting and compacting data, and we'll cover this in a lot of detail. And finally, we will discuss about several ideas of navigating the design space and tuning LSM-trees with some concluding remarks and some open research challenges. Okay, let's dive into the basics. So what is LSM storing? It stores key value pairs. What is a key value pair? It can very well be essentially the rows of a row store, where the value is all the attributes that the row store has, or it can be a flexible schema like JSON, right? And the key is the row ID. but it can also be a blob of bytes that we don't need to worry about what they have inside, and the application on top of our LSM tree actually understands and parses this data. Essentially, what LSM trees are doing is providing the storage level, the storage infrastructure needed for any such application. So what is the basic operation of the basic structure of an LSM tree? It has a memory buffer that accumulates all the incoming data, and the basic storage is actually organized in a collection of levels with exponentially growing size, and we typically use this term size ratio, and we're going to use this symbol T for the size ratio in our presentation. We'll also use a few more symbols, not a lot today, but P stands for pages in the memory buffer, B stands for entries per page, and L stands for the number of levels that the LSM tree has. And note that the L is also related to the total key value entries that we have in our system with a logarithmic relationship with respect to T. So let's see what is the basic principle now of LSM. This is the fundamental thing that LSMs are doing is essentially buffering ingestion. So whenever we have put commands where new data is being inserted into our system, we simply serve them with our memory buffer. So we put 2, 6, 1, 4 as they come into our memory buffer, and this has a maximum nominal size. When the maximum size is reached, this buffer is actually being sorted and is being written to the storage as an immutable file. This through a process called flushing the data from memory to storage. So this leads to low ingestion cost because everything initially was simply stored in memory, and very fast temporal reads, because if we're looking for something that we just read, it will actually be available in the buffer with very high probability. Now, after that, if we focus our attention to the actual storage layer, we have our one immutable file. So this is an immutable file, meaning that we are never going to update it in place. We're never going to be changing any of the contents of a single page of this file. This allows us to have compact storage, so there's no need to have empty, like free space to accommodate incoming updates or inserts. There's no need to keep multiple values, and you can also compress this quite well. And it also allows us to have good ingestion throughput. Why? Exactly because we can sequentially write on our disk, exploiting the sequential performance, which is also relevant even if we have an SSD, because we know that for different reasons, SSDs are actually very amenable to sequential writes, or actually big chunk writes on the device. Okay, now how do we update the data though, right? So if we assume that we have a key value pair with key 6 over here, and we want to insert a new one, we simply put it into the memory buffer. The moment we put it into the memory buffer, it logically invalidates the existing entry in the storage, which was the previously immutable file. When this buffer is full, we're actually sorting this buffer and we're putting into the storage level, and now we have 2 sorted runs in the buffer. This out of place update strategy allows us to have very fast ingestion, because we don't really need to go and reconcile the older values with the new values yet. We simply write them over there without any problem. However, this comes with some costs, right? We have space amplification, meaning that we're storing 2 values at this time, so we have extra storage that we shouldn't, it's not going to be useful actually. And also we have an adverse impact on the read performance. Now, why is that? Because we're actually keeping metadata for all the possible values, irrespective of whether they are valid or not. So we have to keep the metadata available for the invalid 6 as well. So how do we reduce this space amplification and essentially also address to some extent this read performance problem? Well, we compact the two. So compaction is essentially the process of merging 2 sorted runs. It's as simple as that, and it can be 2 or it can be more, as we'll see later on. But through compaction, we actually are able to create fewer sorted runs and alleviate most of the space amplification that this out of place paradigm creates. So if we assume that our level 1 now has compacted and has a couple of files, a couple of entries, sorry, if a new buffer comes from the top, it will eventually be compacted with existing files in level 1, and Now we'll see that this grew beyond a nominal threshold. So in the beginning of the talk, we saw that the LSM tree has essentially these exponentially growing sizes where the expected size of every level is predetermined. And it's a function of the size ratio, which is a tuning parameter, and the size of the buffer, which is yet another tuning parameter. Right, so when level 1 grows beyond its nominal size, then it has to be moved on to the next level. Logically, this movement is only logical. We don't really copy or write anything at this point because that was empty. We only need to change the manifest of the LSM tree to say that whatever was here is actually now in level 2. If more data come into the buffer will be full. Eventually, it will be flushed on level 1. And then if this keeps happening, level 1 will still compact the files, and then eventually it will grow beyond the nominal size, and then we'll have to move this level 1 to level 2. We will compact these two files, and then we'll push everything to level 3. As we will see, this process of full compaction is only one way of doing things. So, but we'll speak a little bit later about another way of partial compaction. So through these periodic compactions, we create this LSM tree that has the shape of exponentially growing sizes, which allows us to essentially address to some extent the space amplification problem and to make reads better. So by not allowing to have multiple sorted files per level, essentially we only have to perform one search per level. However, this design overall adds right amplification, which is one of the problems, not problems really, but one of the characteristics that LSM tree have, and we should try to keep pushing onto reducing the right amplification with respect to the design of LSM trees. Putting everything together, the sizes are given by these very simple equations. So P times B is the size of the buffer, P pages times B entries per page, and the size of every levels are increasing with an exponential way with a factor of T every time. All right. So how about querying now? So remember, we have this structure of the tree where we have sorted files, sorted levels on storage, and we have this buffer that is also getting any incoming data. When a query comes, the query can be on the form of give me the value of a specific key. In this case, we're requesting the value of key 7. The first thing to do is that we go to the buffer. If what we're looking for is in the buffer, then we're done. This is great, and our query goes very fast. If the buffer does not contain what we're looking for, then we have to start going into the storage and start essentially searching each and every one of the files. So if we don't have any additional metadata, we'll have to do a binary search in every storage layer, essentially performing a logarithmic number of storage IOs for every level. And we'll do this even if we don't have the value we're looking for in any of the levels, because we don't know which levels might contain 7, as long as the minimum and the maximum of every level contains 7. All right. So eventually here we're going to go to all 3 levels. We're going to find nothing, and when we go to level 4, our binary search will actually get us our key that we're looking for. So can we do better? Let's see. The first thing is that we can try to think how we can avoid this logarithmic search, and this is easily done through a simple thin layer of indexing, which is typically called fence pointers, and essentially it's a zone map. So every level here has a zone map, and it allows us to quickly do the binary search in memory by storing the smallest key per actual storage page that the level has. So now, instead of actually performing our binary search on storage, we'll go to the fence pointers, we'll do the binary search in memory, and then we'll go to the single page that might contain value 7, if that exists. And even if the value 7 does not exist, if a page contains the range that contains 7, we'll have to still go fetch this page and check whether 7 is there. So we'll do the same for every one of the levels, essentially doing only one IO per level, and eventually we will find 7 in the last level. Now the cost has reduced dramatically from a logarithmic search for every level to one search for every level, and the number of levels is also given as a logarithm of the total data with base T, which for short we will say L in the remaining of the talk. Right. So, but just as a reminder, the read performance cost here is essentially log n with base T, where n is the total data size. All right. Now, can we do better? We can still do better, right? We can avoid these unnecessary IOs. These IOs in level 1, 2, and 3 can be avoided by using additional metadata. So what state of the art is doing is essentially we augment the design with Bloom filters. So Bloom filters are essentially membership test data structures that allow us to know whether a key is part of a set or not. So now, when we're building a level, we're actually also populating a corresponding Bloom filter. And when a query comes, we first ask the Bloom filter. If it says no, we never go to the fence pointers or to the storage. We do none of these accesses, and we completely skip this cost. Of course, a Bloom filter, as you may know, might have false positives. And if it has a false positive, we will go and we perform this unnecessary I/O with a low probability equal to the false positive. And in the best case, the Bloom filter will also give us a true positive. It will tell us I have 7, and we'll go to the specific page to read the value that we're looking for. Okay, the false positive of a Bloom filter is typically given by an equation that is essentially, we need to focus on these two parts: the amount of bits that are allocated to the Bloom filter and the amount of elements that are actually indexed in this Bloom filter. So this ratio, bits per element, is the one that controls performance or accuracy, let's say, of the Bloom filters. So in many systems today, we can see tunings that have 10 bits per element for the Bloom filters, which leads to a false positive of about 1%. And with respect to the size ratio, practical systems have also tunings between 4 and 10 across the different levels, which actually is a classical decision in many production systems. All right. So what is the cost? The cost now is essentially 1 I/O per level with a false positive probability phi, which is much, much smaller than the previous cost that we had before. Okay, and as I said before, the false positive is much less than 1. So essentially, we really optimize the query performance through the use of Bloom filters. Now, how to manage memory? So in this discussion here, all of a sudden, we started adding different parts in memory, and there's a question of what to do with them. So do I make sure that everything is always in memory? What if I don't have enough memory, right? So this is what is actually being managed typically with a version of a buffer pool, which is called block cache in LSM-based systems. So what block cache is doing is essentially it keeps in memory the most useful blocks of the filters and the indexes. And in fact, if we see most of our practical implementations today, we'll see that the Bloom filters and the indexes are actually part of the files on storage. They are stored with the files and written in storage, and they're not necessarily in memory the first time I'm asking query. So when a query comes, let's say, again, we're looking for 7, after visiting the buffer, it will go to the corresponding level, and it will fetch in memory the buffer pages, the buffer pool pages, and probably the index pages to search what it's looking for. And it will keep doing that in all of the other levels. And in some cases, it will also bring data pages as well. So essentially here, this is a special type of buffer pool that has Bloom filter pages, it has index pages, and it also has data pages. And in many systems today, there is a discussion about how to prioritize, how to really make this block cache work. It's a key point of optimization in today's systems. We'll speak a little bit more about that later. So what about range queries? So a range query of the type, essentially give me all the keys between 9 and 90, cannot make use of Bloom filters. The Bloom filters are designed only for point queries. So instead, we'll still use the fence pointers to actually point us to the corresponding pages per level. And now we know that these are the pages that I have to read. Of course, there might be some values to be trimmed in the beginning and the end of this range, but I know that I have to essentially merge these, in this example, 4 sorted runs to give the result back to the user for the values between 9 and 90. All right. What now? Right. And the cost analysis essentially here, the performance really does not depend a lot on the shape of the tree. It rather depends on the data, on the amount of data that we want to read, because it doesn't matter the fact that we have multiple levels. Approximately the amount of pages we'll be accessing is depends on the selectivity of the query, and also a little bit on the amount of invalid data that might exist here, and the efficacy of the k-way merge that we have to do. Now, what if we have a short query? So it's only a short range, and we're looking for values of keys between 9 and 15, where essentially all of the qualifying values are essentially only in one page, or mostly in one page per every level. So for every such short query, Bloom filters can still not help. However, the performance now is not query dependent, is essentially tree dependent, right? Because we have to do at least one IO per level, we will essentially have a cost of L, where L is the number of levels for the tree. So depending on our work, we already see the intuition here. Depending on our workload, different parts of the tree might interest us a lot when optimizing the design or not. So there's a lot more optimizations that are on LSM trees. I list here several of them. I'll quickly touch upon them. So essentially, when we're talking about read performance, we can work on making the trees to offer simply to be faster. For example, using cuckoo filter that has been shown to be faster than Bloom filters in some setups. This is work from SIGMOD last year. There's also work to reduce the memory size of the filter tree, or sorry, of the filter data structure, because memory is becoming relatively more expensive than storage and CPU as we're deploying in larger data centers today. So this is work published in ArXiv about reducing memory utilization. There's also work about reducing the CPU cost of LSM-tree, sorry, of probing Bloom filters and essentially calculating hashes. Essentially, there the idea is that we want to increase parallelism, so we want to cram more queries with the same CPU, and we can avoid some of the hashing. And this is work from Damon last year. And there's also, we talked about range queries, and we saw that Bloom filters cannot help. However, there are variations of filters that are targeting either medium-sized range queries or short range queries, really, to further optimize and completely avoid some of the levels, similarly to what Bloom filters are doing that have been proposed in SIGMOD in the last few years. With respect to the index pages, there's not a lot to be said, really, because indexes are essentially, the index information are essentially helping us to avoid doing the binary search on storage. However, we can still work by codifying the indexes in a slightly more efficient way, or by using learned approaches to perform the search in a way that we actually perform faster memory search compared to binary search. Finally, regarding the block cache, I think the most interesting difference of the block cache when compared with the buffer pool is that the reason to evict pages from the block cache is not only the capacity. We evict pages from the block cache every time we perform a compaction. So every compaction invalidates all the pages of the previous sorted runs that were compacted. And they have to be evicted from the buffer pool because they have no physical meaning. So this means that it's very important to prefetch, not necessarily because new pages that we don't have in the block cache are useful, but because pages that we just had in the block cache have to be evicted, but the data that was there are actually very useful. And there's work from VLDB a couple of years ago that proposes ideas to prefetch, and that's actually very important. And similarly to that, there is also work on pinning specific pages that we don't want them to be lost from block cache at all, or also prioritizing differently the pages when they come from the indexes or from the filters or from the data. So essentially the prioritization here says that we want to give high priority to blocks and indexes compared to data, because without blocks and indexes, we cannot find the data anyway. All right, so that concludes the first part of the tutorial. And now I'm going to hand over to Subhadeep for the second part about optimizing ingestion.
So hello, everyone. So my name is Subhadeep, and I'm a postdoc at Boston University working with Manos. Thank you, Manos, for the first part of the presentation. So now that we know about LSM basics, in this second part, we will actually look at the different hybrid and new LSM designs that were proposed from academia and also from the industry that would make LSMs more optimized for ingestion. So in this part, we will particularly focus on the different ingestion optimization techniques of LSMs. So if you recall, an LSM has two parts, one in memory, which is the buffer, and one on the storage, where we have most of the data in terms of the different sorted runs. And first, we will look at the different buffer optimizations that we will have in terms of how we can make ingestions better. First, we look at the implementation of the buffer. This plays a key role in how much in terms of throughput we can gain when we are ingesting data. Classically, a buffer has been implemented as a vector. So when we are ingesting data, we can simply append them. And appending data, as we all know, is really cheap. And also, it does not require us any extra space for storing the data in memory. However, if we are going to execute a mixed workload on a vector implementation of the buffer, we would have to scan the entire buffer because there is really no order of the entries in the buffer. If we want to avoid this log big of n cost, we will have to sort the data as we insert them. Once again, that would make ingestions quite expensive. And in our experiments with mixed workload, we have seen that moving from ingestion-only workload to a mixed workload actually reduces the performance of ingestion in buffer by 1 order of magnitude when we have a vector implementation. So many LSM systems actually use lightweight index like what skip list does. And yes, it has a slightly increased cost for ingestion. We have log n cost for ingestion at this point, but having this lightweight index over there allows us to have good query performance. So we can use this express ways over there to find our target data, which in this case was 7. So all these data structures that we use to implement the in-memory component of LSM-trees can help us tune the performance and extract better ingestion performance based on a workload. So these data structures, each of them navigate the read-write memory trade-off in their own ways, but if we know the workload, we can really have our best implementation and extract near optimal performance. For example, if I have a ingestion only workload, or I have a workload where I do not really care about the tail latency for reads, I might as well go for a vector implementation. On the other hand, if I have a mixed workload where reads and writes are interleaved and I really care about the tail latency of all the operations, I would rather go for a skip list. And lastly, if we have some extra CPU horsepower to spend because our workload is IO bound, we might as well go for a hash map based implementation of the buffer. The size of the buffer, that is the mem table as we often refer to in case of LSMs, also plays a critical role in determining its ingestion performance. So here in the slide, you can see we have two buffer sizes, M1 and M2, M1 being smaller than M2. So with a smaller buffer, when we are ingesting data, the buffer gets full relatively quickly. And what does that mean? We already know that if the buffer is full, we have to flush it to disk. So having a small memory buffer would actually mean that we are flushing the data frequently to disk, which also means we are compacting data more frequently on disk. So this frequent flush is not always desirable because it also induces write stalls. So it stalls the pending operations that are going to happen in the database in a future time. Also, because in practice, the size of the memory buffer and the size of the files on disk bear a 1-to-1 correspondence. Smaller size in the mem table also means that we are having more number of files on disk. So there is an overhead that we induce in terms of maintaining the file metadata because we have now more number of files. And lastly, for a given size ratio, we will have a tree that is slightly longer in terms of the number of levels. And as we know, if we have more levels, our read becomes probabilistically more expensive. So what happens when we have a really long buffer, really large buffer? Now the buffer is large, so it can host more number of entries. And by keeping the entries for a longer amount of time in memory, we can actually facilitate queries faster, especially if the query workload has some temporality, we can serve them directly from the memory without going to the disk. So it has its own benefit. Again, we will now probably have a smaller tree because each level is also proportionately larger. So smaller a tree on disk means we will have better point and range query performance. However, if you look at the flushing of the buffer. Yes, it is infrequent as compared to what we have when we had a smaller buffer. But every time we flush or every time we compact, we are compacting a larger amount of data. So there is an extra overhead that this large buffer size induces, and this can be particularly harmful when we are executing tail latency sensitive workloads. So in practice, it really depends how we want to choose our buffer size. It can be as small as 4 kilobytes, very small really, one page, or it can be maybe half or one whole gigabyte if that permits. But in most practical use cases, we find the sweet spot bit of the buffer size between 2 megabytes and let's say 128 megabytes. So this is where the sweet spot for the buffer size remains. And lastly, we will talk about the number of buffer components that we retain in memory, and we will see how this particular aspect of buffer design affects the ingestion performance. So in this case, we assume that we have some extra memory because we have already seen that having a large enough memory buffer might not be helpful in every use case. So instead of flushing the data when the mem table is full to the disk, what we do is that we turn the mem table, sort the whole data that all the data that we have in the mem table and store it in memory, because we now have some extra space, as an immutable mem table. And we keep on doing that as long as we have the capacity to store the immutable buffers. Storing the buffers in memory without flushing them to disk has twofold benefits. One, now we have more amount of data in memory. That means our queries can be faster, especially if they are temporal. And secondly, because we are not accessing the disk very frequently, we can actually absorb a higher pressure for writes because we are just simply keeping them in memory. And at a later instance of time, when there is not much pressure in terms of ingestion, we can compact all these immutable buffers and write them back to the disk. So lazy flushing has its own benefits. It can help us avoid write stalls, absorb high pressure of writes. But of course, as we discussed, it requires a little bit of more memory because we are now storing more immutable buffer objects in memory. Okay. So that brings us to the different optimizations that we can have in terms of implementation and design of the memory buffer to facilitate fast ingestion. But remember, most of the data in an LSM tree are actually storage resident. LSM tree at its core is a disk or storage based data structure. Right. To be more specific, if we are looking at a tree that has a size ratio of 10, typical industry values, and maybe it has 4 levels, 99.9% of the data is actually storage resident. So more than how we design the memory, it really matters how we store the data on storage if we want to attain superior ingestion performance. So let us look at how we do that. In fact, how we store the data on the storage actually influences not only the ingestion performance, but it also influences the query performance as well as how good we are utilizing the storage space that we have. Great. So we begin with the data layout. And until now, in the whole discussion that we had today, we talked about leveled LSM tree. So leveled LSM tree is generated by eager merging of the mem tables when they are flushed from memory to the storage. What do I mean by that? Let us take this with an interactive example. So here we have a small buffer over there. Size of the buffer doesn't really matter, but we have a buffer over there, and when the buffer is full, we flush it to the first level on storage. The next time the buffer is full, we flush it, but we make sure when we are flushing it, we are also compacting with all the data that is already there in level 1. Once again, the buffer is full, we keep on repeating the same thing. This applies to all levels on storage. And what happens as a result is that we have only one sorted run per level. What do I mean by that? Each sorted run in a level is completely sorted, so we can do binary search on that. Also, there cannot be any duplicate in terms of the key that we have in one particular level. Of course, there can be duplicates across levels, but within a level, there cannot be any duplicates because we are merging them in a very eager way. This way of merging data in an eager way allows us to have better read performance, especially for point queries, actually also for range queries, because we have a limited number of runs that we want to have to probe or have to access when we are returning the query results. Also, because there are no duplicates over here, it offers a great utilization of the storage space. So we have really small space amplification. However, the problem is that every time something was flushed, we kept on merging things. And by merging, it meant we are reading things from storage to memory, doing the whole compaction thing, and then again writing them back. So this requires a lot of superfluous IOs to the storage. So merging frequently has its benefits once again, good for reads, but not so good in terms of the write amplification. We are writing the same data over and over again. So in 2008, if I remember correctly, Apache came up with a different design for LSM trees, where they said we will not merge our data eagerly. So what happens here? When the buffer is full, we flush it to disk, we have one sorted run. But the next time the buffer is full, we flush it to disk, but we do not compact with the data that was already storage resident. So we keep on doing that. We do not perform any eager merges over here. And our LSM tree would look something like this, where instead of 1, we have now T runs per level. So we have T times more sorted runs overall in the tree. We can guess the benefit. The benefit is, of course, we have superior ingestion performance because we did not merge a lot of data upfront. But we now have an increased number of sorted runs. And remember, there can be duplicates in each of the sorted runs in terms of the keys. So we have a poorer space utilization. So we have an increased space amplification. And for queries, we now have to probe more number of sorted runs on average. So we have also a poor query performance. So at one end, we had, so bigger notation wise, you can see the size ratio actually plays a role over here. We can see, you can see that the leveled design has a read cost that is T times cheaper as compared to its tiered variant, whereas the tiered design has a write cost that is T times cheaper than the leveled variant. And space amplification wise, there is a factor of T square between a leveled and a tiered LSM design, tiered having a higher space amplification. Right. So now we have these two LSM designs. One is really read optimized, the leveling one, and one is really write optimized, the tiering design. And these were essentially the two classes of LSM data layouts that we had with us maybe until 5 years from today. And since then, with the work from Diane et al. And some work from Facebook, we were introduced to hybrid data layouts. So here, the levels in an LSM tree do not have to follow the same merging eagerness. So here you can see the first level here is tiering, while all the rest are leveling. Here we see an opposite pattern. So let us look at these two hybrid LSM data layouts take a closer inspection. Okay. So let us start with rocks, the rocks to be proposed one leveling strategy. So what happens here, we have the first level that can contain up to T sorted runs. This is good for a particular class of workloads. Let's say I do not want to frequently merge my data when I'm flushing them from memory. So I do not do that. I retain them. And when we retain them, we are not incurring any frequent write stalls that compactions would have otherwise incurred. Most importantly, as Manos pointed out, because we have block cache in memory and compactions actually evict all the data or filters that you have in the block cache, by not merging or compacting data eagerly in the shallower levels, we are retaining the state of the block cache. And by doing so, we can facilitate queries in a much better way. So one leveling in its own use cases has its benefit. Diane et al. In SIGMOD 28 came up with this alternate design, if I may call it so, where they introduced the L leveling, where the last level is leveling and all the other levels that the LSM has is tiering. So they can have up to T tiers. The good thing here for this design is that if you recall, there is a size ratio of T between these levels. So each level is T times larger than the previous one. For T equals to 10, this last level in this LSM would hold 90% of the data. And most of the queries would actually terminate here if we are assuming a uniform distribution. And that means by not having this level implemented as a tiering and allowing this to be there as one single sorted run, we are really cutting down on how many runs a point lookup is probing, right? So we have the benefits of a tiered design on top. So we reduce the write amplification because we are not merging eagerly, but by having the largest level as leveling, we are also helping the queries. And there we have the design of the whole continuum of the data layout. So now the question remains is that I understand we have all these designs for the storage layout, but how do we choose when I'm building a storage engine? How do I choose which data layout is optimal for my workload? In fact, choosing the correct data layout given a workload in terms of maximizing the performance is a very tricky job. It is a non-trivial job to say the least. More so, the data layout and other data layout reorganization related questions in commercial systems are actually hidden in the black box of compaction. So as users or developers, we see that an engine supports us with one or several compaction algorithms. But because this is a black box, it is very hard for us to understand what is going on underneath the hood of compaction. So what are the different design questions that are being answered? Is it only the data layout or something else? What else is going on? So in our work from last year, which was published in VLDB, we broke down this compaction black box in first order primitives. So we identified the key design questions that constitute any LSM compaction strategy. And these are, firstly, how do I lay out the data on the storage? Secondly, when we are performing compaction, how much data are we moving at a time? Third, if we are moving part of a data from a level, which part are we going to move? And fourth, when exactly or what events exactly are responsible for triggering a compaction in LSM engines? And the answers to these four questions gave us the four first order compaction primitives: the data layout, the compaction granularity, the data movement policy, and finally the compaction trigger. Out of these four, we have already discussed about the data layout and the continuum of data layouts that LSM may have. So let us now understand a little bit more about the rest of the three, beginning with compaction granularity, which essentially drives the amount of data that we are going to compact during every compaction job. And until now, at least for an LSM design, we have seen that when a level is full, we choose that level and compact it with all data from the following level. So all data from these two consecutive levels are fetched to memory, compacted, and then written back. And this is still a very valid valid compaction granularity, which is consecutive level and used in asterisk DB. However, there is a big drawback to having a compaction granularity that is this large. Let's see that with an example. So here, remember, we have capacities for every level, and let's assume that we have an LSM tree, which is more or less in a stable condition. So at this point, what happens when the memory buffer gets full? If the mem table gets full, we flush it down, but now after compaction, the first level is out of bounds. So we have to move data down. And when we move data down, we move all data from that level. So we move that down. And once again, level 2 is now out of bounds. And these keeps on going until we find the level that can actually store the data. This kind of cascading compaction in practice is very expensive in terms of as you saw, you are actually reading all data that was on the storage to memory, compacted them, and then have written them back. So it incurs several IOs to the storage. And while this whole operation is happening, the other operations are actually stalled. So there is a huge latency spikes. We have unpredictable performance because of this huge latency spike, although it might be infrequent because this case is not very regular. But whenever that happens, there is a huge spike in the latency. Thus, to avoid this, many practical systems like RocksDB has resorted to a partial compaction routine. Here in partial compaction, we do not anymore compact whole levels at a time. Rather, we only pick a few files, maybe even one file from a level when a level is full. And once again, we will see with an example how we do that. So again, our compaction granularity now is files, and let's see how that works. You can see at the beginning that in every level, we have several files, and the files are separated by this white line that we see. So now, when the mem table is full, we compact it. We have 3 files in first level. But instead of moving all 3 files from this level, a partial compaction routine would choose a single one. We choose this file and merge it only with the files from the next level that are overlapping in terms of the key range. So we do not need to merge it with the entire all files in the subsequent level. So we do that. Once again, we now have the second level out of bounds. We choose a file from this level and compact it with the 3 overlapping files from next level. And we continue to do so until we have an LSM tree that is stable. By compacting file at a smaller granularity, we do not necessarily gain in terms of the amount of data that we are moving. There are some optimizations which I'll talk about later on, how we can gain in terms of write amplification, but we moderately move the same amount of data. But the main advantage of partial compaction is that in every compaction job, I am actually moving a smaller and more stable amount of data. So the amount of work done per compaction is amortized across all compactions. There is no particularly large compaction that will take a long time. And this allows us to offer predictability in terms of performance. Right. And finally, we have our third compaction granularity, which we see in our tiered LSM design. So in tiered LSM, rather than going for the size of the level, a compaction is triggered based on the number of sorted runs that we have in a level. So here, when the buffer is full, we flush it to the first level. The first level has 4 tiers, which is exceeding the limit that we had, which was 3, as you can see. So we compact all the runs in that level. Remember, until now, whenever we did a compaction, compactions happened between data from 2 different levels. But in tiering, it's different. We compact all the data from the same level together into a sorted run and write it back as one new sorted run in the following level. So this is the key difference between how a tiered LSM does compaction in terms of the granularity, as opposed to how a level variant does that. And there we have our 3 options for compaction granularity. This is definitely not an exhaustive set, but this is a very good representation of what happens in LSMs in the industry. Now, moving on to the third compaction primitive, which is specifically for leveled LSM designs with partial compaction. For this part, kind of LSM design, there is a second question that we must answer. Because we are not compacting all data from a level, rather we are only compacting only part of it, maybe one file. The question remains, which file should I choose to for compaction? And a very naive way to do things would be I pick a file at random, or I can even pick a file in a round robin manner. In practice, round robin has some benefits because it guarantees certain properties, but there is no particular data performance metric that it optimizes for. So many storage engines actually look at the files from the from the target level and looks for the file that has the minimum number of overlapping files in the next level. This way, they can cut down on the high write amplification that LSMs are known for. Also, we can choose. So we can keep some metadata about how many deletes or delete tombstones each file is containing, and we can choose the file with the highest density or highest number of tombstone in that. This way, we ensure that deletes are propagated to the last level of the tree and are persisted in a timely manner, also helping us with reducing space amplification. And for read-friendly designs, we can always choose the coldest file for compaction. This way, we can retain the hot data blocks in the shallower levels of the tree, and that means those blocks will be hit earlier, and we can our queries can benefit from that. So that is the data movement policy, which brings us to our last compaction granularity, the compaction trigger. And until now, we have seen, especially for an leveled LSM design, level saturation has always been the trigger. Whenever a level goes out of bound, we trigger a compaction in that level. For tiered, it was the number of sorted runs. Whenever that goes out of bound, we triggered a compaction. But we can actually have our own compaction trigger and trigger compactions based on the metrics that we want to trigger them on, right? So for example, in some implementation for RocksDB, in their implementation of what they call universal compaction, they keep track of the estimated space amplification of the tree. And by doing so, they compact a level, they initiate a compaction whenever the space amplification in a particular level goes beyond the threshold. We can also keep track of the age of the files in a tree. And if a file is in a level for too long, we can force trigger a compaction on that file. This way we make sure that all data are compacted, and particularly for the requirement of timely delete persistence, this makes a lot of sense, which we will also see a little bit in the third part that Manas will be talking about. Right, so we have now our 4 compaction primitives, and what we want to put forward as a key takeaway over here is that any LSM compaction algorithm can be actually presented as an ensemble of these 4 compaction primitives. Not only that, you can even come up with your own compaction algorithm based on your workload or performance target based on these primitives. So here you can see we have done this work, and we have had several systems implementing several different compaction strategies, and we see how we can break down them into the compaction primitives. For example, RocksDB with one leveling has a compaction trigger based on level saturation and file staleness, and it compacts data with a smaller granularity of 1 or several files, but not the whole level. And it has several file picking policies for the partial compaction routine. At the bottom of the screen, you will see *DB, which has both leveling and tiering, but for leveling, it compacts data based on the level saturation. But when it does not do a partial compaction. It compacts whole levels at a time. Next, we have HBase, which is a strictly tiered design. And this is one example of tiered LSMs that we have in the industry. And finally, we can see LSM-Bush, which is a paper from the academia, which has hybrid leveling. So some levels may have, which are on the top, might have a tiered implementation, while the others might be leveled. And based on what the implementation are in each level, we have the granularity of compactions. We actually have a very cool demonstration of a dictionary for compaction, Compactionary as we call it, in SIGMOD this year. So it's on Tuesday. We have 2 sessions between 11 a.m. and 4 p.m. And what you can do in this demo is that you can actually look at how different state-of-the-art LSM compaction engines perform. This is a live demonstration of how the files are getting compacted in each level. You can as well create your own compaction algorithm and play around with that. So if you are interested, please visit us during our poster session, during the demo sessions itself. Okay, so now we understand that compaction affects more than just the ingestion performance of LSM engines. In fact, it touches upon several different key performance metrics. And it is very important for us to understand what's going on underneath the hood of compaction engines, but also try and optimize compactions in the interest of performance. So there have been several lines of work that has attempted to do so, both from industry and academia alike. So beginning with background compaction. So background compaction, the concept is really simple because in partial compaction, if you remember, when a level is saturated, it will trigger a number of compaction, and this will go through all levels of tree. So what many systems do is that they have a thread pool, they spawn a bunch of threads, and when the compaction is triggered in a level, they actually place the threads in a way so that they are non-blocking with the ongoing writes and reads in the database, but at the same time, they can take advantage of the parallelism that the threads offer. So doing compactions as a background job using background threads makes a lot of sense, especially in production systems. Next, we have compaction priority. Many systems, in order to preserve the data integrity, assign writes, that is the ingestion that is actually happening through the database, a higher priority than compaction. Because if you think of it, compaction is a database's internal operation. This is not, it is triggered by the external operations, but it is what the database does. So we do not want to lose out on the raw performance that a system wants to offer. So when there is a lot of pressure, we do not perform compactions. Rather, what we would do is that we would retain the flushed mem tables in the first level and not merge them eagerly. Although it is a level design, we are not merging it whatever there was eagerly. We are just simply retaining them as a tiered, just like what a tiered LSM would do. And sorry, because I just went out, press something else. Okay, we are there. Okay. And by prioritizing writes over compaction, we can actually absorb a lot of write pressure that is a case, especially when we are dealing with bursty ingestion traffic. And when the write pressure goes down, we can once again use our favorite background threads to move these tiers or sorted runs to their correct position. So this way, the tree becomes out of shape for a time being, because between the first level and the second level, we do not maintain a size ratio of T anymore, but we are able to absorb a higher pressure for ingestion. And third, we have an IO scheduler. So this work was proposed by Balmau et al. And what the idea was that instead of allowing the different operations of LSM to use the bandwidth as they want, they had an IO scheduler that partitioned the device bandwidth and let them and assigned different parts of the bandwidth for ingestions to the databases, flushes from mem table, and compaction. They also prioritized the flushing of the data in the shallower levels, because typically they are moving a smaller amount of data. And by doing so, by prioritizing flush and compaction at the shallower level, and by using a scheduler to separate the IOs, they attain a higher throughput for ingestion. Right. And now in the final part, we will talk about the different approaches that entail data placement, but also allows us to have a better ingestion performance. So if you recall, as Manos pointed out, an LSM tree typically stores key value pairs in every level. But there are several use cases. In particular, if the value field is really large, the tree will be really large. Every compaction will actually compacting more amount of data. So what Whiskey, this paper from Liu et al. Published in FAST, what Whiskey does is it separates the keys from the values. So in the tree itself, it stores the key pointers, so no values. So now the key becomes smaller because a pointer is typically much smaller than a value field. So the write amplification is reduced significantly. And this pointer actually points to the value which is stored on the storage. Now, there is an argument that this might increase the random read costs. But if we can do it in an SSD conscious way, shredding the value across several chips in the SSD, we might take advantage of the properties of the SSD itself and have a better query performance. So we are reducing the write amplification in the actual tree, but at the same time, using the properties, benefits that SSDs offer, we are gaining in terms of query performance. So overall win-win. And in this final part, we have a different way of positioning data. So partitioning and sharding. So in partitioning, this is done in PebblesDB. What they do is that they have the same LSM tree, but in the same LSM tree, they have logical partitions based on the key range. So if I have, let's say, in this level 0 to 10, the first tier would store 0 to 33. The second tier would store 33 to 80. The third tier would store 80 to 100 and so on. So by logically partitioning the keys, the LSM tree, what they attain is a superior, is a lower write amplification, because they are not merging all data from in different partitions, but the mergings happen only within a single partition. So every merging has a reduced write amplification. And exactly the same thing has been adopted in Nova LSM, where they are operating on a distributed environment. So instead of having logical partition, we actually now have physical partition of data, where the 3 different LSM trees based on the partition are stored in 3 physical storage. And by doing so, we can take advantage of the parallelism that the device might have to offer and have better performance. Okay, so I guess that brings us to the end of this part of the talk. We began by looking at the different main memory optimizations, design choices that we had. Namely, we talked about the different data structures, the size of the buffer itself, and how we can have lazy flushing strategy as opposed to an eager one to enhance the throughput for ingestion. Second, we looked at the storage layer optimizations. We talked about the whole compaction design space of LSMs. We talked about how we can tune and come up with probably even our new compactions in the interest of performance. And finally, we talked about the hardware conscious designs or the data placement based designs, where we had SSD conscious designs that would help us have better ingestion performance on SSDs. And then in a distributed environment, we can either go for a sharding or partitioning based scheme. So that brings us to the end of this part, and I will once again hand it over to Manos for the last part of the talk.
So let's go to the last part of today's presentation about navigating the design space. That by now we have seen a very good deal of what this design space looks like. And essentially, LSM-trees is a very classical paradigm of a data structure that can be highly tuned between its read performance, update performance, and its memory space footprint. And we have seen different ways that we can actually navigate these performance trade-offs. So here, for example, by choosing between tiering and leveling, or the hybrids between them, and by changing the size ratio, we can navigate this performance curve where we can be more write optimized if we reduce the update cost over here, or we can be more read optimized if we reduce the read cost over here. And actually, if we use carefully our available memory, we can further push the line down and reduce the cost of read performance, so of read queries. So how to optimally allocate the available memory is one of the key questions that has been asked over the last few years. And this was this work that we did with a paper called Monkey, where essentially we're using workload and memory budget to actually answer two fundamental questions. So how to allocate memory between buffer and the Bloom filters, and how to allocate memory among the Bloom filters in memory. So if we go back to our LSM structure here, we have the Bloom filters, and in the worst case, when we have a query that doesn't find any values in the database, right, we will perform at most 1 IO per level with a false positive probability. However, if we look closely, what we observe is that the last level is exponentially bigger than the other levels, and it only helps us to avoid 1 IO. So this gives us an intuition that maybe we can actually take some of the memory from the last level and reallocate some of these bits to the top levels. And with this small change in the false positive of the last level, and small increase of the false positive in the last level, we can have a significantly decrease of the false positive of the top levels. So this approach was proposed in SIGMOD 2017, and essentially it changed the fundamental assumption that the Bloom filters have the same tuning across all levels, and it allowed different levels to have different bits per element, essentially, for the Bloom filters, which actually through an optimization, we saw that we were actually having an exponentially decreasing false positive as we're going towards the smaller levels. And if we do the math, we see that essentially this does not have the logarithmic factor of the number of levels anymore in the cost. So we have we are saving the whole logarithmic factor from the cost, and actually the benefits will be further bigger as the data increases, as the data size increases. So this work, along with, this served as a building block, along with an analysis of quantifying the read cost as a function of the data size, of course, but also the index, the memory allocated to indexes, the memory allocated to the Bloom filters as a whole, and the memory allocated to the buffer, and the write cost as also a function of the data size and the memory allocated to the buffer. So if we have these two costs, and there is probably a little bit too complex to solve all the equations here, if we have these two costs, we can actually formulate an optimization problem. So given the workload, which could be, for example, how many read queries writes, how many range queries, what is the selectivity of the range queries, how many updates, and so on, we can actually figure out how to distribute the available memory that we have between the buffer, the filter, and the index. So there is another side to that problem too, though, because in this analysis, the block cache was not taken into account. So another approach that was presented in SIGMOD and LDB a couple of years ago, it actually tries to do essentially the same thing by calculating the read cost as a function of the block cache size and the buffer cost, and the write cost as a function of the buffer size. So now we can still have an optimization problem. We can still find the best tuning between the memory allocated to the buffer and the size of the block cache. However, this assumes that the memory allocated for the Bloom filters and the memory allocated for the index is fixed. So it still remains an open and very interesting problem to see, can I actually co-optimize all of them if I have a fixed memory budget for me, because in reality, the memory budget is strict for the whole system. It's not about only half of the system. So this is still, I guess, an open problem. It would be very interesting to try to have a holistic tuning about memory allocation across all different possible components of the system that require memory. And in fact, there is one more that is a little more subtle. So when we are performing compactions, we also need memory buffers. And when we're performing range, when we're answering range queries, we also need compaction buffers because we compact on the fly for the range queries. So there's actually a few more nuances to really achieve holistic memory tuning. Now, if we switch gears to the design continuum, we saw before the leveling to tiering design continuum, and with the one leveling and the L leveling, and essentially we can now abstract this further and consider that every one of those designs can be defined with essentially two numbers. One is the size ratio, and one is how many levels of these three are actually leveled and how many levels are tiered. And we can actually create a bigger continuum of hybrids where we can vary, even at runtime, the number of levels that are tiered if we have, for example, write pressure in our system. And this is a first spectrum of continuums that we can get across a very read optimized on the left-hand side to a very write optimized on the right-hand side. Another way to create to create a spectrum that navigates the read versus write trade-off is to change the number of sorted runs. So here we allow different levels to have their own decision about how many potentially overlapping in key range sorted runs I might have. And if I allow this, then I'm also navigating a read-write performance trade-off, which is somewhat different than the actual trade-off that we saw before with the hybrid levels. And the third continuum, let's say, is the one that allows us not only to have different number of runs per level, but also allows us to have different size ratios. So if we allow the size ratios to dynamically change, we can actually adapt to the specific workload whenever this is needed. And this creates a third spectrum where we allow variable size ratio, and we can actually achieve, we can vary our design to be more read optimized, to be more write optimized. So overall, there's a huge continuum of designs in LSM, and it is still very well a research question how to optimize and how to adaptively change our design through any of these spectrums at runtime in order to get the best, not only with respect to performance, but also with respect to other metrics like most notably write amplification and space amplification. Now, when we're doing performance modeling, we're using workload and the performance targets that we might have, and we're using a cost model, right? So we're using cost models. So what are these cost models? Essentially, they are worst case cost models. And what do I mean by that? So worst case performance modeling, for example, if we have a point query, it assumes that the answer would be on the last level, which means that in the actual equation, the cost of this query is 1 IO for the last level plus a false positive for each one of the other levels. And then all the optimizations, all the decisions about how much memory I'm allocating across my different parts of the system is using such assumptions, not only for the read queries, but also for the write queries and any other part of the system. Is this always accurate, right? What if the actual 7 we were looking for is on the top level? Okay, one could say yes, but this is exponentially less frequent. But in the classical analysis, we never take that into account. So in fact, there is an average case performance modeling that says I actually will try to quantify more accurately where my in this example where the query will land, so where the query will terminate. So when I'm calculating the cost, I will include in my math the probability that the answer of a query is in a specific level, which can be done, for example, by using the distribution of the data, the distribution of the queries, but also the sizes of every levels to quantify this probability. And then I can have a more accurate model that I can use to perform average case modeling. So that type of work is also presented, will be presented, I guess, later in VLDB, but actually by 2 separate papers. But essentially, one of those is using average case performance modeling to perform a more fine-grained optimization that allows to make real decisions about budget on the cloud. So now, if we have more faithful, I would say, modeling about what the cost of our operation is, we can actually have a better estimate about how I should spend my budget, and then get the best design, the best hardware that my budget can buy, and then maybe even the best provider according to the different prices that every provider has. So another aspect to that question of average case of performance modeling is what happens if workload changes, right? So all of our analysis up to now, it's doing classical tuning. All of the papers that we have described and we have cited is doing classical tuning, which means what? Which means that given a workload in a data set and the internals of the data system, find me an optimal tuning T. So this is a meta parameter with multiple tuning knobs, essentially, that minimizes the expected cost, where expected cost is a cost model that takes into account the tuning and the data distribution. What if there is unpredictability in the workload? What if I expect a workload W, but what comes to me is something around a sphere, let's say metasphere, hypersphere, I should say, around W, right? Is my tuning going to be optimal anymore? The answer is no. So another type of tuning is called robust tuning that is also going to be presented as a first effort later this summer at VLDB, where the idea is, now I know that I have a data set in the workload, but I also know that there is a region that my workload might come in with some probability anywhere in that region, right? So now I don't want to find the minimization. I don't want to minimize my cost model. I want to find the one that actually gives me the closest to the optimal performance whenever the workload comes anywhere in that sphere. So this is essentially a min-max problem, and it actually gives some interesting results where, for example, as we're increasing the workload noise, here the x-axis is increasing the workload noise, we can see that while the nominal cannot achieve any speed up, there's no benefit or there's no change really when there's noise, the robust type of tuning, actually the higher the noise that we get, the higher the benefit that the execution gets, which it can be up until 3x or even 4x if we anticipate for higher noise, and higher noise comes. Of course, you might observe that this comes at a cost. So there is some instances. So every dot here is essentially an instance that is executed, a different tuning instance. So there are some instances that they get slightly worse performance, and this is the price to pay for unpredictability. But for the majority of the cases, we have significant performance benefits. So probably the last type of research trend that we'll try to discuss today is what about deletion, is the impact of deletion in LSM-trees. So I'm switching gears now and going back to the internals to see how deletion is being taken care of. So look at this LSM-tree. It has a level 2 and a level 3. These are different files, right? And this is a key value entry of value of key 5 that actually invalidates a previous entry of key 5. And let's say that I now want to delete 5 entirely from the system. What do I do? I don't do anything here, right? There's no in-place deletion. I insert my tombstone in the buffer, and the moment this tombstone is inserted in the buffer, it actually invalidates any prior instances of 5. And in order to actually get rid of 5, this tombstone has to propagate through periodic compactions and physically be compacted with that, and at compaction time, it will get rid of the older value 5. And when the tombstone reaches the last level, we can also get rid of the tombstone itself. Right? How about queries now? So if a query comes in and looks for 5, it will actually go to the storage. So even though we're looking for a deleted entry, we'll have to go to the storage. So here, 5 is a special key value entry where the value signifies that it's a tombstone. So essentially, it is also indexed in the Bloom filter, and of course, it can be found in the corresponding pages through the fetch pointers. So our query will actually say yes in the Bloom filter, and then we'll fetch this page, which might be already in memory, of course. It will fetch this page to simply to read the tombstone. Now, are deletes frequent? Are deletes a problem? In fact, yes. So this is from production. There's millions of deletes per day in large-scale production systems. So ZPDB is an internal system in Facebook, and UP2X is also doing 92% of the merges is happening because of deletes. But it's not only because of the workloads, it also comes from internal operations. So every time we are using as our storage engine an LSM-tree, and the application does something like a table drop or data migration or even periodic cleanup, this translates into deletions, either point deletes that we saw here or range deletes that are slightly more complex. But on top of that, there is another reason to worry about deletion, which is the privacy guidelines that come through regulation these years, where essentially different legislation like GDPR and CCPA and more are actually requiring that the systems that we deploy in the wild should return back, should guarantee that the data is deleted within a set amount of time. So timely deletes is indeed a research challenge for LSM-trees. And here, a couple of years ago, we actually did some work that provides this feature of timely deletion in LSM-trees by changing the compaction trigger and the file picking policy, which are two of the four fundamental questions that Subhadeep was talking about before. So if we change the file picking policy to make it the age of the tombstone, so if we know that when a tombstone is too old, it has to be compacted, and this becomes a trigger, I should say, for our compaction, then we are becoming able to guarantee timely deletion. And then if we have to pick which files to move, now instead of picking files with very low overlap between this level and the next level, we're picking files based on their tombstone density and based on whether they have an expired tombstone inside. To give you a visual example here, if we have our tombstone here, this has a maximum time that it can stay in level 1. So the moment this maximum time is expired, it has to be moved on to the second level. If it is moved because of other compaction operations, then it's all good. We're actually great. And every level has its own different time to live for the tombstones in a way that the sum of these levels is actually equal to the threshold. This is the delete threshold that the application or the legislation actually imposes on us. And it's also been proven that the optimal way of allocating this time across levels is actually exponentially increases with the size ratio T as well. So this is the work that we need to do for the system layer of handling deletes. And there has been also some analysis on how does the requirements that the law provides transform how does the policy transform to requirements? And here we essentially has retention-based deletes. We have retention-based deletes and on-demand deletes, and also some support for at the application layer where we need to extend the SQL to be able to express this timely these time constraints to the storage engines to be handled in the system layer. Right. So essentially, this is we're getting towards the end of the tutorial. So I would like to take the opportunity to summarize a few high-level concepts that we discussed today. I think one thing that is very clear is that the LSM design space is vast. There is a lot of tuning that needs to be done. There is a lot of different designs that we can actually utilize. And also compactions are very important to essentially to any performance metric, but also to optimize for ingestion-friendly systems. But I would like to stress even more than anything that tuning the system is not only very important, but it is still an open problem. Similarly to traditional database systems, LSM-based storage engines have an increasing number of knobs, right? Maybe you've seen some papers that say that MySQL has and Postgres have already something like 300 or 400 knobs. LSM-trees are lagging behind, but not too much. Now we have hundreds of knobs in LSM-trees, and it is becoming a crucial question how to tune these knobs. So there's a lot of open research challenges. Let me touch upon some of them. So one thing which is still important is to reduce write amplification, because whatever we do in LSM-tree, what happens is that we write our data again and again through compactions. So can we avoid some of these compactions? And then if we do so, do we hurt some of the other metrics that we care about, like maybe deletion requirements or performance? So this is one question. Another question is to make our compactions and layout workload aware. So today, some of the tuning is workload aware, but essentially the decision about compactions is it's at deployment time. It's a fixed decision for most trees, for most practical implementations. They have some adaptivity oftentimes, but it's not changing the the compaction strategy, it changes a transient behavior. So actually, there is a lot of room for innovation, both into making workload-aware optimizations and decisions, about compactions, but also maybe thinking even harder about this transient behavior when workload changes. And this is related to stability of performance, right? So we saw before, we discussed before that through these periodic compactions, we might have peaks and valleys of performance because we have write stalls, for example. So this is still an open problem, and essentially performing holistic tuning, but also figuring out how to deal with these transient write spikes, for example, is a very important question moving forward for LSM-trees. As I was saying before, automatic tuning and adaptive behavior, this is probably the least mature part, like area of LSM-trees that we're currently. And we need to understand how we can harness all these different tuning knobs, all these different, let's say, flexibility that the tuning knobs are bringing into making automatic decisions as well for deploying our LSM-trees, but also focus on adaptivity of our design as the workload has cycles or changes over time. And last but not least, we talked a little bit about deletes, and essentially this guaranteeing that our systems are following the privacy regulations and other constraints that are coming from the application / legislation side is actually very important, and it opens avenues for research. So throughout this tutorial, we mentioned a few papers, but also we have cited plenty more in our. Thank you for your attention, and I'm happy to take any questions you might have.